We just saw conceptually what acid-base reactions might look like or look like as particles. So now we're going to do some calculations related to those acid-base reactions. So in an acid-base reaction, we're going to have an acid. In this reaction here, this H is going to be the acid proton, and then we will see a base, hydroxide here. Just to put this into words to connect it to the last slide, this is our acid. This is our base, and anytime I react those two, I get a salt, which is just going to be a cation and an anion, and then I get water, and both of these are going to be more neutral than what I started out as, okay? Which makes sense even with the colors here, right? The other thing that I get besides my salt and water is I'm going to get some heat. We could talk about the heat in these reactions, but we're just going to look at quantities for now. So with this experiment, this is one that you'll see demonstrated in your lab as well. We take KHP, which is a solid, and we add water to it here in this flask. And then to that KHP, we're going to add barium hydroxide. And there's lots of different ways you can use this setup. Remember, this was called a burette, and this is an Erlenmeyer flask. So this is a burette, and this is an Erlenmeyer flask. These flasks are really good for swirling solutions around without it spilling out, so that's what the angled sides are good for. So here I'm going to add a base to this KHP, and you can see that here. Here's that solid KHP, and then we're going to add some base to it. Now, neither one of these are actually colored in lab, so we'll use an indicator to visualize when we've got equal amounts of them. But in this type of experiment, you would want to estimate ahead of time to kind of plan the experiment out. So if you want to use about 15 mils of this barium hydroxide, and you've made it up, you don't have a lot of significant figures on it yet, and we want to get better sig figs, but I know it's about 0.2 molar. What mass of KHP should you use? So if I want to use 15 mils, and I know the concentration, how much solid should I put in the bottom here? So let's go ahead and work this out. We've worked these out before, but it's just under a new label of acids and bases. I forgot to highlight my base here. So I have, let's change that to a 25. So 25 mils of my barium hydroxide. And my goal is to get 2 grams of KHP. So I know that somewhere along the way here, I'm gonna need to use a mole ratio, right? Because I'm switching chemicals. So somewhere in the middle, I'm gonna need a mole ratio. But let's work our way there. Right now we have mils of the barium hydroxide. So 1 mil is 10 to the negative 3 liters. And now one of the other first things you might want to do is write this out as 0.2 moles barium hydroxide per 1 liter. Makes it look more like a conversion, right? And I can take that conversion then, and I can plug it right down here to help me convert liters barium hydroxide into moles barium hydroxide. Once I'm at moles of barium hydroxide, I know that has to follow down here to the denominator. And this is where I can switch to moles of KHP. So if I want to switch chemicals, I want to use my mole ratios to help count. 1 barium hydroxide reacts with 2 KHPs. And then I look at my goal, which was grams of KHP. It's our lucky day because there's a molar mass over here. Remember, KHP isn't actually potassium, hydrogen, and a phosphorus. It's this larger molecule. We just abbreviate it. So follow your units down. Moles of KHP, grams of KHP. This is 204.22 per mole. I got that from right here. And so when I do that calculation and look at my sig figs, I'm going to have 2 sig figs, so 2.0 grams of KHP. So this tells me, right, this is my KHP, my acid. This tells me if I want to use about 25 mils of my solution, then let's put about 2 grams of KHP down here. So your next task is going to be to do the actual experiment. This was the planning stages here, but now when you actually do it, you would go weigh out your solid, your KHP, and lo and behold, it uses about the right amount of barium hydroxide that we were hoping, and then you'll be able to find the molarity of this barium hydroxide. The idea here is that 2 sig figs isn't really very good. 3 or 4 is better. So if I can use a lot of significant figures, very precise and accurate mass, then I can improve that 0.2 molar and get more significant figures for that molarity. This is called standardizing a solution. So you're adding significant figures or standardizing this barium hydroxide solution. So you can give that one a shot now or in class. And then we will move on to another calculation, very similar, but this time we're going to, again, standardize, but we're going to use one solution to standardize another solution. So you can see that the equation is a little bit different now. We're going to take some HCl with a lot of significant figures. So maybe on the first scenario here, if this is 1 and this is 2, on scenario 1, we're going to have a very precise amount of HCl here in the flask. And then we've got sodium hydroxide, and I need to find the molarity of that. So the sodium hydroxide will be in this burette here. So if we titrate 25 mils of this HCl solution, let's immediately write this as a conversion. With exactly 14.55 mils of sodium hydroxide, what is the molarity? So I'm going to be looking for molarity equals moles over liters, right, for the sodium hydroxide. So I've got information about HCl to start with. From there, I will be able to get a better set of significant figures for this chemical. And let me switch this to KOH instead. Sorry, typos here. So this should be KOH. So 25 mils of this. So let's start with that 25 mils of HCl. 1 mil, 10 to the negative 3 liters. And then 0.1566 moles of HCl per 1 liter of HCl. I need to get to potassium hydroxide because that's what I've got in my equation here. Should be a K. And so moles of HCl and then moles of KOH. I can grab my coefficients. Here they happen to be very easy. They're all going to be 1s. And so if I can do this calculation, then everything's going to cancel except for moles of KOH. And I want to keep an eye on significant figures. Here I have 4 significant figures, and here I have 4. So when I do this problem, I want to keep all 4 significant figures, 0.003915 moles of KOH. Now, molarity needs moles over liters. I have mils of the KOH, so 14.55 mils. Let's convert that to liters. Divide by 3, so 123.01455 liters of KOH. All right, from up here. So molarity is going to be 0.003915 moles over 0.1455 liters. And that comes out to 0.2691 molarity. Don't forget to put the solute with it. So that's going to be KOH solution. Stop and think about this a little bit. It's especially easy when I have a 1-to-1 ratio. So I had 25 mils of 0.15-ish molarity, and then it took less of the KOH to equal the moles of that. So if it took less of the KOH must be more concentrated. So less of the more concentrated to equal the amount of protons over here. And sure enough, this concentration of the KOH is higher than the concentration of the hydrochloric acid was. So that's one example of solving for molarity here. Here's another similar example where it's going to be the opposite scenario. You're going to have the sodium hydroxide here, and you'll add the hydrochloric acid to it. So give that a try and be able to do these acid-base reaction stoichiometry problems. And that's it for the whole semester. So way to go.